Again, this is the simple example with a Keras program. You have seen this already, the main changes shown in green here. And if I open the tutorial, oh, and let me show you how to get here actually, so that you can see the flow on the website. So if you land on the GraphCore website, you will see the top menu and then the developer section here. On the developer page, you have a bunch of tiles here, documentation, model garden, and GitHub in general, and the examples here. Some downloads are in these two tiles. Pop Vision tools separate from the core software downloads. So to get the latest SDK, for example, you will be able to go here and download it from there. In the examples repository, it's organized by the machine learning domain, GNNs, NLP models, speech and vision, and we will be using tutorials for this section here. In the tutorials, there are some simple applications, feature examples, code that we referred in the blog posts, and tutorials, which are almost step-by-step guides for different frameworks. For example, in Poplar, we have 6 tutorials that take you from the basics on variables, then introducing some more complex concepts here, but everything is very simple, as I've mentioned before. And if we look into TensorFlow2, you will see Keras, for example, which offers a description of what needs to be done to a program to port it to the IPU. And the code is very similar to what I had in the slide and in VS Code as well. So we have a simple, well, MNIST example. I think it's the original from the Keras tutorial. Loading the data and splitting the data into loading the train and test sets, defining the layers. So in this case, it's a functional implementation, functional version of the API. We create a model that has some inputs and outputs here as the inputs and outputs of this function. And we run the compilation here and fit the model, which is the main training loop, and then we run evaluation on the model. I will skip the summary and then highlight the steps to port this example to the IPU, described very openly here. Importing the IPU specific module in Keras, and then one of the steps that we want to have, given the requirement that the communication on the IPU needs to be scheduled during the compile time. And this is also a requirement for XLA that we use with TensorFlow. TPUs also require statically compiled graphs in terms of tensor shapes. In order to enable that, we add these few lines to the code. What these do is making sure that the data set, as we iterate through batches, doesn't end up with a batch that is not full, not complete. So the last batch in the data set, if the data set size is not divisible by the batch size, might be incomplete, and the last batch, instead of being of batch size 16, can be smaller than that. And that would require a different computational graph. So a way to do that can be either to loop through the data, repeating it at an item level, or to simply truncate the data set by a small number of items there to make sure that length is divisible. So we add that code to the example, and then we configure the IPU system as shown here. Again, selecting one IPU, and an option that I didn't show previously is this on demand, meaning that it will not allocate the IPU until you actually start executing the engine. Otherwise, it will allocate the IPU and keep it for your program when you create the graph, or actually when you configure the IPU system in TensorFlow. And then similarly to my previous slide, we create the IPU strategy, which is based on the core distributed strategy concept in TensorFlow. And we put the computational graph. We tell TensorFlow to put the computational graph instantiation and execution inside the strategy scope. And after that, we will see that the model runs on the IPU. For example, you should be able to see the graph compilation as a part of the execution. So if I try to open that in VS Code, let me open another window here, which is exactly the examples. It would be let me go to the TensorFlow Keras tutorial once again. It will be this demo code only, the final example that has the IPU constructs in it. And also, as a part of this repository, we have a couple of demonstrations of optimizations and pipelining as well. So if I compare these two, so not these two, no, that's probably a mistake. If I take completed demos and compare the demo starting point with demo IPU, I should be able to see the basic changes. So just importing the IPU Python module, making the dataset divisible by the batch size, which is taken care of in these lines, configuring the IPU system, and then making sure the graph runs on the TensorFlow IPU device. So this is one thing to get a Keras program to run. And then one of the optimizations that is used here is this loop on the device, which in PyTorch is called device iterations. In Keras, there is a standard construct called steps per execution that Google has created for TPUs as well. And it's just another argument in the model compile code for training and for inference. And then a couple of other things shown here is pipelining and replicated execution. Let me highlight those in the tutorial README. So in the examples repository that we have, all the examples and tutorials have a nice README file that describes what's going on and steps we need to take to run a program. And by the way, if you find some imperfections here, please let me know. We'll fix it quickly, typically. So this is probably what we covered already. The replication is simply done when we set number of replicas to 2, and when configuring the IPU system, we auto-select not 1, but 2 IPUs. And that's typically enough to run across several IPUs in a data parallel way. You will also need to make sure that the dataset size is divisible by the global batch size, which now is batch size times number of replicas. And pipelining is another concept that we use to fit larger models, to run larger models across more than one IPU. It's a kind of model parallel execution where, for example, we have 3 IPUs as in this picture, and then the layers of a model are distributed across the 3 IPUs so that the forward pass goes, a batch during the forward pass goes from the first to the second to the third IPU, computing the activations. And then during the backwards pass, it goes back. So we put the weights of these different layers across the different IPUs as shown here. And if we did only one batch, it would be inefficient because, well, most of the time, most of the IPUs are idle. In order to avoid that compute bubble, we put more than one batch in, and in the pipeline. And there is some pipeline fill and pipeline drain phases that are small and that can be amortized as we increase the number of batches that are processed in a single engine call here. And the gradients are accumulated from all the batches that are processed here. So you can see, well, the second batch will be processed in this set of blocks as shown here. And in order to pipeline a program, as you can see in the completed demo here, you configure the number of IPUs, number of replicas maybe, but then you can associate, you can use this with constructs when you define your computational graph and allocate specific operations in your Keras TensorFlow graph to pipeline stage 0 and then pipeline stage 1. So the steps to enable pipelining after this declaration will be taken care of by TensorFlow and Poplar for you under the hood. And there is a way to apply pipelining to a model without changing the source code of the models. So you do not have to explicitly modify the source code of a model. You can do it in a separate script by iterating through the layers in Keras and associating layers with different pipeline stages. So this is on porting Keras programs, and I will now go into PyTorch. But any questions so far? I can see in the chat there is something.
Yeah, there's one that I put an answer on about migrating a model that was trained on a GPU to an IPU. And so if you have anything to add to my answer there.
Yeah. So it's typically straightforward. You just take the weights. Say, if you are in Keras, you can model save the weights from any other accelerator, CPU or GPU. And then on the IPU, you can model.load the weights, and you can construct a graph in your script. And this is a typical way of doing that. And vice versa, the model trained on IPU, you can save the weights and use it on a different accelerator. There is interoperability interoperability, I should say, between us and the world. Okay, thank you for the question. So moving forward, another set of tutorials is in this PyTorch realm. And in the slides, I just want to show that I have the links here. If you download the PDF, I guess I have only 5 minutes left. So the basics are covered here, and it's very similar to what I had on that slide showing the training model and inference model in, let me see if I have it. In PyTorch. Maybe I will just go through the README really quickly. So anything interesting other than that? Well, the loss function, the computation of loss is a part of the forward pass because we use it to build the backwards pass after we extract the computational graph by tracing the model. There is a limitation here. The conditionals, as in other tracing approaches, will not be mapped correctly. We are working to enable a special operation to leverage actually the underlying branching that Poplar supports. But as far as I remember, we do not support that currently in PyTorch. Data loaders, I have covered those. Then we instantiate an optimizer in PyTorch using the PyTorch module. And with these, if you use the kind of graph core specific, IPU specific optimizers, you typically have some ways to tweak the performance a little bit better, and maybe control the data types that the optimizer is using. For example, for Adam, the first and second order momentums will be stored potentially in FP32 instead of FP16, which is beneficial for numerical stability. And then detaching from device, after you train the model, you can reuse the same IPUs and detach from device to run the evaluation on that model on the inference graph loaded to the same IPUs. So, and there is a notebook associated with this tutorial that you can run, and that will produce some nice outputs, including the visual ones. In terms of mixed precision, there is a tutorial here that discusses that, of course, running in a lower precision can be faster. I think the ratio on bow is 4:1. So the theoretical FP16 flops are 4 times higher versus FP32 flops. And we support these 2 precisions on bow in terms of floating point precision. So this tutorial discusses that you can deal with numerical stability by doing loss scaling, and we support automatic loss scaling in PyTorch. Stochastic rounding is helpful, and Chad mentioned what it is. So when you're accumulating millions of tiny values into a large FP16 value, you will not lose precision when you run on IPU, and it's supported at the hardware level. But in order to run with a lower precision, you just do model.half as shown here. And when you are creating your inputs to the model, you can cast those to the lower precision as well by running .half on them, on the inputs of the model as well. And then again, for the optimizer, you can control the loss scaling manually or automatically. And for Adam, if you go into the documentation, you will see some options to control the precision of the optimizer state. Stochastic rounding can be enabled explicitly. And for matmals, you have control over the partials at the low level. So what is the type of the results when you do the dot products in the AMP unit, the matmal units? And I think this is the essential part here. We have also pipelining part for PyTorch, which can also be done with modifying the source code to explicitly say these layers go to these pipeline phases, or you can do it after the model is created. And there is a tutorial on how to observe the values of tensors as you execute a model and how to load the data efficiently. I think we are out of time now for this session. Thank you very much.
There are a couple questions that we can answer there. So I'll hit the second one first. I think that had been missed above. So if a replication factor is not used in the same microbatch, can the microbatch size remain the same? And I think Alex said the microbatch size is independent of replicas, that our global batch size is basically microbatch size times replicas, or microbatch size times gradient accumulation times replicas. But the microbatch size is really dependent upon how much you can fit in the IPUs from a memory standpoint. And then, is there any maximum value in replication factor? Really, the maximum value is the number of IPUs there. So if you had a model that fits on a single IPU, the max is going to be limited by the hardware configuration. So that would be 64 with the Argonne system. Theoretically, we could have a 1024 one, but there's not one that anyone has like that right now.
Yeah. So in order to the effective batch size to remain the same when running with a higher number of replicas, you will need to run with a smaller per replica batch size. And arithmetically, it will be equivalent. And I guess that can be an experiment for strong scaling in this case. So I'm happy to discuss it.
Yeah, and then the other question was about main difference between GraphCore and Cerebras. So at a high level, of course, they have everything on one wafer. But if you look at it logically, there's a lot of similarities of many independent cores. Their individual cores aren't as, don't do quite as much as one of our cores do. They've got, I think, 850,000 of them on their chip. Their amount of memory per core is a lot smaller than ours. I think they're at 48K, we're at 624K. So that's some differences in there. So ultimately, like, the amount of SRAM we have across a rack is more than they have. It's just spread out across multiple chips instead of all on one chip. And for now, we try and fit everything a lot more in that memory. I know they've been talking up a lot their Memory X system, and they can do more external memory than we can at this point when you go out to DRAM. But we think for when things fit into SRAM, we have we think a better sweet spot there at a lower cost. but a lot of similarities that just kind of the independent cores and SRAM kind of state.
And a year ago, Argonne has published a paper on, well, comparing the systems that are present in the leadership compute facility. GraphCore, Cerebras were a part of that paper, and it compares the performance across several models and benchmarks. So please feel free to refer to that paper for some details. And again, the call to action, please apply to the allocation program, as Murali said, and please join the community in Slack that we have.